for introduction, and thank you organizers for the invitation and giving the opportunity to talk here. My talk will be mostly a review talk of relatively old stuff, but luckily we had this morning excellent talk of Tian Yang on some recent development. So I didn't know that he will talk about this, what he talked about. So my talk will a little bit overlap with his. So unfortunately, you will be disappointed because my overview will be worse than Tian's. Okay. Anyway, so here is my. Okay. So the motivation is. Given by two directions in three-dimensional topology, given by hyperbolic geometry and quantum topology. And the main question, the most important question in my mind, what is the relation between the two? And in more generally, so in quantum topology, the biggest question, the topological or geometric interpretation of quantum invariance. So in this light, so the relation between hyperbolic geometry is just a particular case of this big equation. And from physics side, it's a question of quantum gravity in 2+1 dimensions. So my outline, so I will talk about just the knot theory a little bit, the quarter of time, and then I will give an overview of volume conjecture, but it is unfortunately outdated compared to what Tian Yang talked this morning. And then I spend half of time on the Teichmüller TQFT. So this is the older version of the TQFT, which Tian explained this morning, and hopefully they complement each other. And then I briefly discuss the further perspective using the framework of the Teichmüller TQFT. Okay, so knot theory. I exclude from the beginning the links, so I will consider only knots, and the knots will be open knots, which I call long knots, oriented from the bottom to top, which I call in extremity and the out extremity. And here two examples of long knots. But this is trivial knot, but for me it will be important certain property which I call normality of the knot, which means that the local extrema should be always oriented from right to left. Namely, I don't want to have the maxima oriented from left to right, like here, or minima oriented from left to right. So the normalization procedure is a procedure of removing this unwanted extrema by applying a Rademacher one type move. In principle, you can do either this one or with the opposite crossing. It doesn't matter. And the normal diagram if there are no such such extrema. And in particular, the normal diagram always consists of even number of crossings. And then when we have a normal diagram, then we have 4 types of segments and 8 types of crossings, because the vertical direction will be a distinguished direction for us. And all crossings are put in a generic position like letter X to avoid strictly vertical segments. So in this way, we have these 8 possibilities altogether. And now let me discuss the algebraic input. So I'm going to use normal diagrams as a combinatorial encoding of knots. And now I want to put some algebra to use this combinatorial input in the form of diagrams to extract invariance. And for that, I need R matrices. So what is R matrix? It's a vector space with an invertible linear map on the tensor square of this vector space, which satisfies this Yang-Baxter equation in the braid form. So I attended yesterday OpenCore's talk where he talked also about the R matrices, but he talked about the spectral parameter dependent R matrices. And here it's important to stress that there are no spectral parameters. So these are constant R matrices. And then, let us, there are infinite dimensional R matrices, which are also interesting. But for topological applications, there are not easy things to work with. So here I'm going to discuss only finite dimensional R matrices. And then for make the construction explicit, we pick up a basis in the vector space and the corresponding dual basis. And the important thing is so-called partial transpose. So R matrix is as a linear map in the tensor square of V means that graphically it is described by a full-leg object. And the partial transpose when we turn down and turn up a pair of legs. And it is defined for any linear map from V squared to V squared. So the result of partial transpose becomes a map from the tensor product of the dual space times V to V times tensor product. And the most convenient way to see this operation is drawn here. So the F with 4 legs, it's drawn in black. And then the turning the legs, 2 legs with blue color indicating the dual vector space. So this is the result of partial transpose. And the important property for me of the R matrix is rigidity, which means that the partial transposes of R and its inverse are invertible linear maps. There are infinite class of R matrices which are not rigid. And up to now, unfortunately, I don't know how to use them for invariant constructions. But probably this can be done. Anyway, I will discuss just rigid R matrices. And one of the basic examples, which is most added in quantum topology, is here. So we take a linearly ordered basis. And we use this Heaviside theta symbol, which just says that, which takes 2 values, 0 or 1, depending on the order of 2 arguments. So if A is strictly bigger than B, it is 1, and 0 otherwise. And then we can write a very simple R matrix given here. So, we define its action just on the basis elements. And this theta symbol enters into the definition. In principle, the vector space can be infinite dimensional. It is still invertible solution of the Yang-Baxter equation, but it's rigid only if the dimension of V is finite. So I denote this R matrix by tau P. In 4 slides, it reappears again. So please keep in mind about this example. Okay, so it will be, I will refer to it later on. Okay, so now how we construct the invariance. So essentially, it is a Rishkin-Turaev construction, which is much more general and functorial. And I am adapting the construction just to the context of long nodes. And I'm using the most economical way by avoiding the extreme oriented from left to right. So I have only extreme oriented from right to left. So again, we pick arbitrary R matrix, so rigid, a basis. Then we encode a knot into a normal long node diagram. We denote the two sets of edges and the crossings as EK, CK. And the state of the diagram is just the coloring of the edges of the diagram by the basis elements of the vector space V. And then the weight of the diagram in a state S is just the product of elementary weights associated with crossings. And the elementary weights are essentially the matrix coefficients of the R matrix with respect to this chosen basis. And here I indicate only crossings which are positive. So you remember there were 8 types of crossings, but half of them were positive crossings and another half was negative crossings. And for positive crossings, we associate one and the same weight for 3 types oriented upwards, leftwards, and downwards, which is just the matrix coefficient of the R matrix itself. But for the positive crossing oriented rightwards, so we use double inverse. So what we do, we take the inverse of R, we take a partial transpose, as it is a rigid R matrix, so it is invertible, we take inverse of that. And then we calculate just the matrix coefficient with respect to the same basis. But now it acts in the mixed tensor product of V and V dual. So this is why stars show up here and here. But graphically, it is just this crossing. And for negative crossings, we just exchange the role of R and R inverse. And otherwise, it is the same correspondence. So that here will be R inverse, and here this -1 should be removed. And now we remember that the normal diagram consists of even number of crossings. So if we now count the number of positive crossings and negative crossings, then the difference will be even number of either of positive crossings or negative crossings. So we can always compensate the deficiency by adding a trivial part. Trivial part. Let me just return to here. This is a trivial long node, but it is composed of 2 positive crossings. And we can draw similar thing with 2 negative crossings. So we can just compose long nodes just by concatenating them to balance the number of crossings, to make a number of positive crossings equal to the number of negative crossings. And then we assume that we did this operation. And then we just calculate the state sum. So we sum over all colorings of the weights defined here, but by fixing the input state of the diagram. And then as a result, we obtain a linear map from V to V, which is the invariant due to the functoriality properties of the Richtlichen-Turaev construction. Now, next part, how to find the rigid R matrices. And for that, there are at least 2 approaches. So I will, so briefly, the standard approach through Drinfeld's quantum double construction. It is not confined exclusively to quantum groups. It is more general. It's applicable for any Hopf algebra with invertible antipode. So there is a general way of associating to this input Hopf algebra so-called quantum double, which comes with so-called universal R matrix. And then you study the representation theory of the quantum double on the level of finite dimensional representations. You pick such an representation, and then if you evaluate the universal R matrix at this representation, then you end up with rigid R matrix. So that's one way, and the most simple example is given by UQSL2. But since this scheme uses the quantum double, so we threw away the half of UQSL2, consider just the Borel-Hopf subalgebra, which is presented by just one Q-commuting relation and the two coproducts. So the group like element A, so it is invertible, and skew primitive element B. And if we apply this procedure, then on the level of irreducible representations, all of them are characterized by just their dimension, and the invariant as a linear map becomes the proportional to the identity map up to scalar coefficient, which is identified as an n-colored Jones polynomial. But the way we do the quantum double, namely, we make it as a maximal quantum double in the sense that the dual of algebra is defined as a so-called restricted dual, which corresponds to the set of all finite dimensional representations of the input of algebra. And in this way, this double construction becomes functorial. And this allows us to define the universal invariant living in this space. So this is essentially a double dual. So this O means the restricted dual of D of H. And if you study the construction which I defined in terms of rigid R matrices for all finite dimensional representations, then all of them factorize through this universal invariant. And for finite dimensional Hopf algebras, of course, this double dual will be just identity, so it will live in the quantum double. But for infinite dimensional Hopf algebras, it will live in some sort of completion, which is defined algebraically by this formula. So you do the restricted dual, and then take just algebraic dual of what you have. You lose the Hopf algebra structure, but you keep the algebra structure of the dual space because it is a convolution. It keeps the convolution product coming from the coproduct of this Hopf algebra. But in practice, this universal invariant is difficult to calculate, and I was able to calculate it in the simplest case of this example, where Q equal to 1. So Q2 equal 1, it is just classical algebraic Hopf algebra given by regular functions on the affine group. And if you look at its quantum double, then it has only one irreducible representation, which is one-dimensional. So from this viewpoint, it is this algebra is very far from being a semi-simple, and they're not interesting only from the viewpoint of irreducible representations. But nonetheless, it still gives a non-trivial invariant if you take into account all finite dimensional representations. And the universal invariant happens to be the inverse Alexander polynomial, where the indeterminate argument T is replaced by this group-like element A. And in any finite dimensional representation, A minus 1 is a nilpotent. So the formal power series, which you obtain by expanding Alexander polynomial, inverse Alexander polynomial around 1, truncates to a finite sum. So you still have a polynomial invariant on the level of finite dimensional representations, but the universal invariant becomes an object in a completed algebra, which makes a part of this double dual. So and I expect that for Q generic here, this universal invariant will have something to do with the Habira definition of two-variable polynomial, where Q to power n is replaced by new indeterminate x. Okay, now second approach to producing rigid R matrices, which I like very much because of course, it doesn't give anything new compared to Drinfeld construction, but it is much simpler in my mind. So what is the input? Input now, the braided Hopf algebra. But braided means that the category where the Hopf algebra lives and not necessarily symmetric monoidal category, but a braided monoidal category, which more general. And the second thing, as an input, I pick an automorphism of this braided Hopf algebra. And this automorphism is a kind of something which replaces the representations in the traditional approach. And now for braided Hopf algebras, so that it's much more difficult to write algebraic formulas. So it's much more practical just to draw pictures instead of writing formulas, but they correspond to precise algebraic formulas. And here is a picture. So you should think about maps which go from bottom to top. And for example, here this is the coproduct of the Hopf algebra. This crossing is a braiding of the Hopf algebra. And here the product, the multiple product of the Hopf algebra. So the R matrix is constructed by using the automorphism and certain right action of H on itself, which I denote lambda R, and here is a definition of lambda R. So essentially, if you ignore the automorphism, then it is a Hopf algebra version of the adjoint action. But the presence of the automorphism is important here. Okay, so just a general statement. So if you define lambda R like this, then this solves the Yang-Bak's equation, and it is invertible. Even, but the H can be also infinite dimensional. And now let's come to examples. The most basic example is the braided vector space. So braided vector space is just the vector space with an R matrix. And then given such thing, we can just immediately conclude that the tensor algebra is a braided Hopf algebra. Where degree 1 elements are all primitive. So example, just universal enveloping algebra of Lie algebra. We know that it's a Hopf algebra with primitive Lie algebra elements. This just a similar statement, but you should think about the free Lie algebra built on the input vector space. And we add also this braiding structure. And even more, you can associate in a canonical way so-called Nichols algebra by quotiening the tensor algebra with respect to Hopf ideal generated by primitive elements of degree 2 and higher. Let us see an example. So let us take one-dimensional input vector space where the braiding is given by necessarily just by permutation times a constant, like here. So for generic Q, this ideal is trivial. So the tensor algebra, which coincides with the polynomial algebra, coincides with the Nichols algebra. And if we choose the automorphism just by multiplication with the negative integer power of q, then it appears that the subset of polynomials of degree and less becomes the invariant under this right action, which boils down to the fact that the restriction of this R matrix to this vector subspace is itself an R matrix, n-dimensional R matrix. And as a matter of fact, this happens to be just the n+1 colored Jones polynomial. So you see that how different the way it shows up. We don't need any complicated Hopf algebra. We have just polynomial algebra, simple automorphism, and at the output we have same thing as from UPSL2. And now the most recent work we've done with Mangazeev this year. So now we take the braided vector space, the one which I mentioned the few slides ago, given in terms of this Heaviside theta function, which corresponds actually to a Homfley PT polynomial specified to SLN. And now if we take this as an input here, then the corresponding Nichols algebra happens to be just the exterior algebra over V with no deformation. But as a braided Hopf algebra, it is deformed by parameter P. And then we have a diagonal automorphism given by multiplication of all elements of V by variable T. And at the output, we have a two-variable polynomial, which is conjecturally Links-Gould polynomial coming from the finite dimensional representations of GL UPGL n/1. But the important thing that these are now two-variable polynomial, and the recent works of Neumann, van der Veen, Colli, and Tahar shows that the degree in one of these two variables has a geometric interpretation. It gives a bounds, a lower bounds for the genus of the knots. So in my mind, these invariants are very interesting to explore. And in the light of the volume conjecture, which I'm going to talk about, it would be interesting to study this family, the sequences of R matrices with respect to large values of those integers. And because from one hand side, we know by now that Links-Gould polynomials give bounds for genus. And if the sequences of them can be related to hyperbolic volume, then that would be great, because up to now we don't know invariants which would handle simultaneously the genus bounds and the volume relation to the volume. Okay, now hyperbolic knots. This is just basics of hyperbolic space in dimensions. A hyperbolic knot is just if its fundamental group is realized as a discrete subgroup of PSL2C. We have a rigidity, which implies that the all metric properties of the quotient space with respect to the image of the fundamental group in PSL2C gives a topological invariance, in particular the volume. And this is the simplest hyperbolic knot, which is figure 8 knot with this volume. Okay, so the volume conjecture. This morning we've seen a good, excellent review. Here I just want to mention that, so it's story of colored zones specified to this specific root of unity. And there are few generalizations. This is just part of the generalizations, which is longer, but I didn't have enough space to describe others. But let me point out that the people talking about the volume conjecture always talk about the colored zones. But originally, I define invariance for knots in any oriented complex ring manifolds. It is absolutely the same construction as in the case of S3. But unfortunately, the construction is complicated enough that no example in other manifolds has been calculated. So, but the volume conjecture should be true independently in which manifold you put the knot in. So Murakami they generalized it by replacing volume by simplicial volume. Francois Constantin studied the links in disconnected sum of S2 cross S1s. The more recent generalization is for Witten-Richtlichen-Turaev invariance as a non-standard root of unity. And Tian explained this in more detailed way this morning. And here is my outdated, actually, the list of proven cases. So Tian gave more recent examples. Figure eight knot, so the proof of Ekholm, of course, is the most elegant proof, but I think that I also proved it in the original paper just by using the steepest descent method for the integral one contour integral representation of the. And then the Borromean rings are very similar to figure eight, not in the sense that it is the quantum invariant is given by sum of positive terms. So again, the proof is as simple as the one of Tobias. All knots up to 7 crossings by now are proven by Otsuki Yokota. Torus knots, old story, they have 0 volume. So it was done a long time ago by Tirkkonen and myself. Torus links of this type were handled by Kazuo Hikami. 0 volume links for white-hat chains by Van der Wien. White-hat doubles and twisted links by Zheng. This is, I think, relatively recent. And Constantinus universal hyperbolic links also. But Tian gave, I think, more examples which are more recent. Okay, now I'm turning to second part of my talk, which is more analytic. The problem. So the motivation comes from Witten's theory of quantum Chern-Simons. Here is a brief overview that you pick a gauge group, which is a Lie group, that you pick the 3 manifold. Gauge fields are just one form valued in the Lie algebra of G. You have a huge gauge group given by these gauge transformations of connections. Chern-Simons action, and the classical phase space just it's a finite dimensional space of flat connections on M, and the basic object of interest is a partition function, which is ill-defined because of the nature of the path integral. So the basic question, which is expected to be topologically invariant, and the basic question is what would be the rigorous mathematical definition, which we know in the case of compact groups, which is Richtlichen-Turaev construction in terms of R matrices. But in the case of non-compact groups, so I will explain all the story compared to the story of Tian Yang of this morning. he gave he described today the case which cannot be handled within the framework I'm going to review now. But unlike the Tiang's talk, so he relied exclusively on representation theory to construct his Chicxy symbols and so on. Here I will refer mostly to hyperbolic geometry, how we construct the ingredients. Although they can be also extracted from representation theory as well. So we study two cases of, two cases of interest are isometry groups of hyperbolic plane and the hyperbolic free space. And in the phase space of flat connections, there is they composed of, at least in the real case, composed of many connected components. One of them is of particular interest, which is called the Teichmüller space, which corresponds to faithful discrete representations. And that's what we concentrate on. We just treat this Teichmüller component. And there is a Weil-Peterson symplectic form. So we just try to quantize this symplectic structure by following the principles of quantization coming from the quantum physics, which is called canonical quantization. But since the space is not compact, so there is a challenge coming from infinite dimensional Hilbert spaces, improper integrals, distributional functions. I am going to construct a kind of TQFT, but it is not TQFT in a strict sense because underlying vector spaces will be infinite dimensional. So you should keep this in mind always. In particular, not any partition function can be finite. Okay, so the first thing, the combinatorial input. So it is not just ideal triangulation, it is ideal triangulation with some extra structure, in particular the orientations on the edges, which I call the delta triangulation, which is essentially the delta complex in the sense of Hatcher in his algebraic topology book. So it's a cellular complex where each cell is modeled on the standard simplex. They considered together with phase inclusions. And the essential thing is that so each characteristic map is such that a restriction of this of each characteristic map to its phase is again a characteristic map of a cell of one dimension less. So example, the simplex itself, so it has its faces and the lower dimensional edges. As a whole, it is an example of a delta complex. And this is a notation for I-dimensional cells. And this double index notation is important for the subsequent part of my talk. So it is a second index refers to the, so the first index corresponds to the three-dimensional cell. This I will be 3 in my case. And the second is subcells of the three-dimensional cell on which we model the corresponding cell in the triangulated manifold. And now geometric input. These are just the dihedral angles of ideal tetrahedron. So here is a notation so with 3 index. So to the edges of the 3 cell, we associate dihedral angles of ideal tetrahedron. So in particular, the angles around each vertex sum up to pi, not strictly less than pi as in the case of Tian Yang. Then we have, this is the important part. So when we color all the edges of tetrahedra by dihedral angles, we should identify some colorings through this abelian group action coming from the Poisson action of total dihedral angles through the Neumann-Zagier Poisson bracket. So it means that if you two tetrahedra share one common edge, then the dihedral angle of one tetrahedron can be, part of the dihedral angle of one tetrahedron can be transferred to the neighboring tetrahedron, and without a change of the geometry. And so the balanced edge is when the total angle around the geometric edge is 2 pi. And when we impose for all edges, so this is called the angle structure, which was mentioned in Tiang's talk this morning. And what is important, the equivalence class of such shape structure stays invariant under 2-3 Pachner moves, but not individual colorings. So you have to move in this orbit of this group action. Only after that you can talk about the correspondence between two sides of the angled move. And then we go further. We now define the elementary building blocks. So these are just a tetrahedra with all orientations. We have two types of them, positive, negative, depending on how they are embedded in the usual free space. So you see the difference. So that from central vertex is a source for all arrows, and then the difference between the two is the two edges are oriented in one direction and one in the opposite. And depending on which pair is oriented in one direction, you decide the positive or negative. So here you see that two arrows on the boundary are oriented clockwise, which is positive, and here they oriented counterclockwise, which is negative. We have labelings on faces, which are real numbers, and the dihedral angles, which correspond to shape structure, with a hyperbolicity condition, which is summation of angles around one vertex to be pi. So the alpha 1 plus alpha 2 plus alpha 3 is pi. And the symplectic form of Neumann-Zagier. And now that's important in my mind. So there is a four-dimensional aspect of this theory. Namely, what we do, we take, we look at the 2-3 Pachner move as something going on at the boundary of four-dimensional simplex. So four-dimensional simplex has 5 faces, which are 3-dimensional simplexes. And if we, here is a boundary of 4 simplex, which is a 4-ball. So it's bounded by 3 sphere. And 3 sphere, I look at the 3 space here with point at infinity. And here we see all 5 tetrahedra. So you see that this infinite part, 2 tetrahedra, which share the common face. These are 2 of 5, but 3 others are outside, and they share this common edge 1, 3, and they go around this common vertical edge. So, for example, there is a tetrahedron with vertices 1, 2, 3, 4, which is the outside. We see only the vertices and 2 faces here, and 2 faces given by 1, 3, 2. And okay, I don't. There should be 4 faces. Never mind. That's a boundary anyway. There is a boundary. And what is important, if we look at the dihedral angles of ideal tetrahedra, then they form so 10-dimensional space, because we have 5 tetrahedra with 2 independent angles for each. So 2 times 5, we have 10-dimensional symplectic space. But if we impose the conditions that each edge is balanced, so we impose 5 independent conditions. So this gives a 5-dimensional Lagrangian subspace. But we know how to quantize Lagrangian subspaces. So if we do this, we obtain a 4-dimensional metaplectic topological quantum field theory. which in our case is given by this weight function. So you see it carries the quantum labels on 5 faces. They are labeled by 0 up to 4. And here it is just some Gaussian exponential which realizes the weight function. And this D function enters into the construction of the TQFT, which I'm going now to define. Here it is. So we have this D function times some spatial function, which is given by essentially in terms of spatial function phi sub h bar, which I call Faddeev's quantum dialog, but it's essentially quantum the double sign function of Tian. Same B, but I use h bar for symmetrized combination. And negative tetrahedra given by just complex conjugate weights. So properties, we have a 5-term identity and the tetrahedral symmetries. And the partition function, we just take ideal triangulation with a shape structure. And then we just take a product of weight functions over all tetrahedra and integrate over all phase variables. And old theorem of 2014 tells us that if we impose this topological restriction on the triangulation, then the integral is well-defined and absolutely converging. Absolute value depends only on the equivalence class of the shape structure. And same absolute value is invariant under 2-3 Pachner moves. And here is a simplest example, which is S3 with conical singularities along the wedge of 2 circles. So black edges get identified to one geometric edge with this scalar weight, which is the total dihedral angle. And the blue edge stays by itself, gives another geometric edge with a total angle alpha. And the partition function is the absolute value of Faddeev function. And if h bar goes to 0, we have this exponential decay controlled by the volume of the conical hyperbolic structure on this space. The volume formulae. And then here is the version of the volume conjecture. So in general, we take an equivalence class of the shape structure, and then we maximize the volume, the sum of volumes of individual tetrahedra staying in the same equivalence class. So we try to adjust the representative coloring of individual tetrahedra the way that the sum of the volumes is maximized. And the conjecture is that the growth, decay rate is given by this maximized volume. So the proofs exist. So originally we checked it for 2 hyperbolic knots. Then later it was proven for infinite set of twist knots. Then my student in his PhD thesis considered a case of a knot in RP3. And very recent, Ben Aribi and Wong treated another infinite class of so-called faint triangulations, so admitting some geometric triangulations. And here is a further perspective. So the essential point I would like to stress is that we can go now instead of real line to work with the arbitrary locally compact abelian groups, which is supposed to be self-dual, and then we introduce the Gaussian exponential, which is essentially the quadratic form associated to Fourier kernel, which gives a self-duality of the locally self-dual locally compact abelian group. Then we can write out immediately the metaplectic TQFT in this generalized setting in terms of Fourier kernel and the quadratic form. the Haar measure, and then so the example of the real line, which corresponds to the case I just described, but you can go now to periodic numbers, which are also self-dual. And then you can also generalize the notion of the quantum bilogarithm over such a Gaussian group, which is measurable almost everywhere defined complex valued function, which satisfies this inversion relation, which involves this Gaussian exponential, and 5-term identity, integral identity, which involves this d function coming from 4D TQFT, and just a 5-term identity. Example, this is the prototypical example which I just talked about. There is the generalized version of this given in terms of n terms, n Faddeev dialogues, which we believe corresponds to SL2C Chern-Simons, at least a part of the SL2C Chern-Simons theory. Then there is a 3D index, which corresponds to another example of the quantum dialogue over this locally abelian group. T is a unit, complex unit circle. And this I like very much. This is an example coming from local fields. So you take a local field and you take the abelian group, the multiplicative abelian group of non-zero elements. You take its contrarian dual, and then on it you can identify a quantum dialogue. So I have a 2 years old paper with Garoufalidis where we work out the construction of TQFT along the lines which I described today in the case of real numbers. Okay, thank you. I finished.
Are there any questions? Please.
Yes, you suggested that the equivalent to the colored Jones polynomials for Lings-Gould should not be the colored Lings-Gould, but should be LGN1 associated GLN1.
No. This so you have colored Lings-Gould for G21.
Sure.
Which were what we call VN sequence. So it is what is a nice thing about Lings-Gould, its colored versions, at least the original Lings-Gould coming from GL21, its colored versions are linear, like for SL2, not like for SL3 going like the Young along the Young diagrams or SLN, but it goes linearly, but with step 4. So the dimensions go 4-dimensional, 8-dimensional, 12-dimensional, and so on, but they go linearly. And in this sense, this is just very similar to colored Jones to study. But of course, the R matrix is more complicated. The invariants are 2-variable invariants. But it would be very interesting to calculate in closed form for any color this invariant for particular examples and study the asymptotics.
Yes.
Yes. It is a challenging problem, which I don't know how to approach, but I expect that this will be Habira 2-variable polynomial, but interpreted as an element of this double dual convolution algebra.
There's another question.
So by this linear growth of dimensions for irreducibles of UQGL21, you mean Katz modules?
I don't know how they are called. Probably. I don't know because
the ones that have Clifford algebra inside. But this is just one series. There are other presentations.
I see. Probably these are all irreducibles, right? No?
There are more.
Okay, but they have dimension 4 times n.
Yeah, it's a certain class of.
I see, and they depend also on continuous variable, which gives this extra variable in the polynomial.
Is there another question?
Yeah, maybe one more remark. So, but we approach this our matrices from the side of Nichols algebras, and there is no any other option. We have just those representations and nothing else.
More questions? So I guess then we can thank the speaker
Thank
for
you.
this nice presentation.